Welcome to the Creativity Hub. Today, we embark on a journey into one of the most fascinating and mysterious phenomena in the universe, black holes. What are they? How do they work? And why do they matter? Let's dive into the secrets of the universe and explore black holes. A black hole is a region in space where gravity is so strong that nothing, not even light, can escape from it. They are formed when massive stars collapse under their own gravity at the end of their life cycles. The event horizon is the boundary around a black hole. Once something crosses this point, it is pulled into the black hole and can never escape. The event horizon is essentially the point of no return. At the very center of a black hole lies the singularity, a point where matter is compressed to infinite density and the laws of physics, as we know them, break down. This is one of the greatest mysteries in astrophysics. Black holes come in different sizes and types. The most common type is the stellar black hole, which forms when a massive star collapses. Supermassive black holes, found at the centers of galaxies, can be millions or even billions of times more massive than our Sun. Supermassive black holes are believed to reside at the centers of most galaxies, including our own Milky Way. Their immense gravity holds galaxies together, influencing the formation and evolution of stars and planets. There's also the theory of primordial black holes, which may have formed shortly after the Big Bang. These black holes could be as small as an atom but with the mass of a mountain, and they might still exist today, hidden in the vastness of space. Black holes vary greatly in size and mass, from tiny primordial black holes to the colossal supermassive black holes that anchor galaxies. Despite their differences, they all share the same defining feature, an event horizon from which nothing can escape. Black holes form when massive stars run out of fuel and can no longer support themselves against the force of gravity. When this happens, the star undergoes a supernova explosion, and if enough mass remains, it collapses into a black hole. In some cases, a neutron star, the dense core left behind after a supernova, can be pulled into a black hole if it gains additional mass from a companion star. This process is known as accretion and can lead to the formation of more massive black holes. Black holes can also merge with other black holes, creating even larger black holes. These mergers release enormous amounts of energy in the form of gravitational waves, ripples in space-time that were first detected in 2015. Black holes play a crucial role in the formation and evolution of galaxies. Their immense gravity helps to shape the structure of galaxies, influencing the formation of stars and even the distribution of matter in the universe. The physics of black holes is deeply rooted in Einstein's theory of general relativity. Welcome to the Creativity Hub. Today, we're diving into the bizarre and fascinating world of quantum mechanics. What is it? How does it work? And why does it matter? Let's unlock the secrets of the subatomic world and explore the mysteries of quantum mechanics. Quantum mechanics is the branch of physics that deals with the behavior of particles at the subatomic level. Unlike the predictable world we experience every day, the quantum realm is full of strange and counterintuitive phenomena. One of the fundamental principles of quantum mechanics is wave-particle duality, which states that particles like electrons can behave both as particles and as waves. This dual nature defies our everyday understanding of how matter should behave. The uncertainty principle, formulated by Werner Heisenberg, tells us that we cannot simultaneously know both the exact position and momentum of a particle. The more precisely we measure one, the less precisely we can know the other. In the quantum world, particles can exist in a superposition of states, meaning they can be in multiple places or states at once. It's only when we observe them that they choose a specific state, collapsing the superposition. Quantum mechanics was born at the beginning of the 20th century thanks to pioneering physicists like Max Planck, Albert Einstein, and Niels Bohr. Their work challenged the classical physics of the time and opened up a new understanding of the universe. Max Planck introduced the idea of quanta, discrete packets of energy, to explain why energy is emitted or absorbed in specific amounts. This discovery laid the foundation for quantum theory and earned Planck the Nobel Prize in Physics. Albert Einstein expanded on Planck's work by explaining the photoelectric effect, where light behaves as both a wave and a particle. This duality was a key piece in the puzzle of quantum mechanics and helped Einstein win his own Nobel Prize. Niels Bohr further advanced quantum theory by proposing a model of the atom where electrons occupy specific energy levels. His model successfully explained the spectral lines of hydrogen, one of the first major successes of quantum mechanics. The early 20th century was a time of intense development in quantum mechanics, with contributions from many brilliant minds. The work of Erwin Schrödinger, Paul Dirac, and others helped to formalize quantum theory and make it one of the most successful theories in the history of science. One of the most famous thought experiments in quantum mechanics is Schrödinger's cat. It illustrates the paradox of superposition by imagining a cat that is simultaneously alive and dead until observed. This experiment highlights the strange nature of quantum measurement. The Copenhagen interpretation, proposed by Niels Bohr and Werner Heisenberg, suggests that a quantum system does not have definite properties until it is observed. This interpretation emphasizes the role of the observer in collapsing a quantum superposition into a single state. An alternative to the Copenhagen interpretation is the many worlds interpretation, which proposes that every possible outcome of a quantum event occurs in a separate, parallel universe. This theory, while controversial, offers a mind-bending perspective on reality. Quantum entanglement is one of the most mysterious and intriguing phenomena in quantum mechanics. When two particles become entangled, they remain connected in such a way that the state of one instantly affects the state of the other, no matter the distance between them. Albert Einstein famously referred to quantum entanglement as spooky action at a distance, expressing his discomfort with the idea that information could be transmitted instantaneously, seemingly violating the speed of light. Despite Einstein's skepticism, experiments such as Bell's theorem and the aspect experiment have confirmed the reality of quantum entanglement, showing that entangled particles do indeed exhibit correlations that cannot be explained by classical physics.